Hello science fans! Get ready to explore the fascinating world of electronics. Today, we're diving into the world of RLC circuits, a team of 3 essential electronic parts that form the backbone of countless technologies we use every day. First, we have the resistor, then the inductor, and finally, the capacitor. These components work together in perfect harmony to control the flow of electricity, shaping and directing electrical signals with precision. This makes them absolutely essential for tasks like tuning radios to the correct frequency, filtering out unwanted noise, and efficiently powering countless devices that we rely on daily. Think of an RLC circuit as a complex racetrack for electricity, where each component plays a crucial role in guiding the flow. Each part is carefully designed to shape how the current moves, influencing its speed and direction. The resistor slows things down, acting like a speed bump. The inductor stores energy in a magnetic field like a temporary reservoir, and the capacitor stores energy in an electric field, acting as another type of energy storage device. By combining these 3 components, we can precisely manage electrical energy, controlling its flow and characteristics with remarkable accuracy. Why bother with all this complexity? Because raw electricity, in its natural state, is often chaotic and unpredictable. RLC circuits tame it, allowing us to select specific frequencies, filter out unwanted signals, and smooth out power fluctuations. Imagine if your radio played every single station at the same time, a cacophony of noise and information. Without RLC circuits acting as filters, that's precisely what would happen. These circuits act as gatekeepers, carefully letting only the right signals pass through while blocking the rest. They're the unsung heroes working silently behind the scenes to ensure clear audio, a stable power grid, and reliable communication networks. And the truly amazing thing is that all this magic, all this sophisticated control, happens within a space often smaller than your fingernail. So let's dive deeper and see exactly how each of these essential parts works its magic. Meet the resistor, a fundamental component in the world of electronics. It limits current, acting as a gatekeeper to protect sensitive parts from overload. It also turns excess energy into heat, dissipating it safely into the environment. Next, the inductor, another key player in our electronic orchestra. It's essentially a coil of wire that stores energy, not chemically, but in a magnetic field generated by the current flowing through it. The inductor resists changes in current, smoothing out electrical flow and preventing sudden spikes or drops in voltage. Then we have the capacitor, a versatile component with a unique ability. It consists of 2 plates that store energy in an electric field created between them, acting like a tiny rechargeable battery. The capacitor releases its stored energy in quick bursts when needed, providing a surge of power for various applications. Resistors are like brakes in a car, slowing the flow of current and preventing it from running wild. Inductors are like flywheels, using momentum to keep current steady and consistent, even when the power source fluctuates. Capacitors are like mini batteries, charging and discharging rapidly to provide quick bursts of energy when needed. Together, these 3 components manage energy in unique and complementary ways, shaping the behavior of electronic circuits. The resistor simply opposes flow, converting electrical energy into heat as it restricts the current. The inductor and capacitor, on the other hand, store and release energy, acting as temporary reservoirs within the circuit. They respond dynamically to changes in voltage and current, adapting to the needs of the circuit in real time. This trio forms the foundation of countless electronic systems, from the simplest gadgets to the most complex machines. Each has a distinct role to play in the circuit's overall function, but their teamwork, their interaction and cooperation is what makes advanced electronics possible, enabling the sophisticated devices we rely on every day. Now let's see what happens when we put them all together in a circuit and observe their combined behavior. The real magic begins as we witness the power of these fundamental components working in harmony. When we connect a resistor, which opposes the flow of electrical current, inductor, a coil that stores energy in a magnetic field, and capacitor, which stores energy in an electric field, in a circuit with a power source, we create a dynamic system, a complex interplay of electrical properties. The resistor provides steady opposition to the current, constantly turning some of the electrical energy into heat. The inductor resists changes in current, smoothing out any sudden spikes or drops, while the capacitor charges and discharges, responding dynamically with the alternating current, AC voltage. This creates a constant dance, a continuous exchange of energy. Energy shifts back and forth between the inductor's magnetic field and the capacitor's electric field. Their behavior and the overall circuit response depend significantly on the frequency of the current. At low frequencies, the capacitor effectively blocks the current. It acts as an open circuit, while at high frequencies, the inductor impedes the current flow, behaving similarly. The resistor, inductor, and capacitor each influence the current flow in their own unique way, shaping the circuit's overall characteristics. The result? A circuit that can filter specific frequencies, tune to a desired frequency, and shape electrical signals with remarkable precision. It's not just a simple path for electrons. It's a complex system with its own inherent rhythm and timing. That's the power and versatility of the RLC circuit. Here's where RLC circuits shine: resonance. At a special frequency, the inductor and capacitor's effects cancel each other out. This is the resonant frequency, where only the resistor limits the current. At resonance, the circuit allows a surge of current at one specific frequency, blocking others. It's like tuning a radio to a single, clear station. Push a swing at just the right rhythm and it soars. Same idea here. By choosing the right inductor and capacitor values, we can tune the circuit to any frequency. This lets us filter out unwanted signals or generate precise tones. Resonance transforms a simple circuit into a powerful, selective tool. It's the secret behind much of modern electronics. Where do we use RLC circuits? Everywhere. In radios, turning the tuning knob changes the circuit's resonant frequency, letting you pick your station. Audio systems use RLC circuits to boost bass or treble, filtering sound frequencies. Power supplies rely on them to smooth out electricity for your devices. Communication systems use RLC filters to separate signals. Think Wi-Fi and cell phones. These circuits are the backbone of clean power, clear sound, and reliable connections. The RLC circuit's ability to filter and tune is fundamental to modern technology. From radios to smartphones, they're quietly at work. Three simple components: resistor, inductor, capacitor, make our electronic world possible. That's the beauty of the RLC circuit.